Let's start with electric potential, chapter 28. Okay, so we learned in physics 1 about potentials, and the potential is the work per unit of a unit quantity. So we'll use the same approach and start off with that. So let's say that suppose we have a charge moving in an electric field. Let's see. So let's say suppose we have a charge, and I'm going to use Q. I think in your text, let's see, I'll just use Q. So we are moving in an electric field E. So the charge will experience a force. So the force is due to Coulomb's law. So let's say we have an electric field. So if the charge starts off here, this is an electric field E. So if a charge is over here and it moves from X initial to X final, this position, then it has a force F acting on it. So the force F is equal to the charge times the electric field. And so in going from X initial to X final, for example, the work done is equal to, work done we know is equal to force times distance, of course. So we can write W, the work done, equal to the integral of force times distance, ds, in going from X initial to X final. So this is the work done by the electric field on the charge and moving it from one position to the other. Okay, it's given by force times distance. Once I put the integral, I don't need the W, so I'll take that off. So basically the dW is equal to F dot ds. And when you integrate it, then this is what you have. Okay, so this is the work done on the charge. So we can apply this to uniform fields. So when we get into an electric field, we can use the force due to the electric field. So we can say that in a uniform electric field E, then we have for work W, we can say W is therefore equal to integral from initial to final of Q times E dot ds. I'm just replacing the electric field, the force there by QE, which is the force of a charge, force on a charge by an electric field E. Okay, so I can just replace that. So we can say the work done is therefore equal to QE, and then we shall have X final minus X initial, like that, just for the difference between the two. So if you like, we can put it down as delta X. So we can say W is equal to QE delta X. And so if we wanted to find electric potential, so electric potential energy, so we can change it to electric potential energy by using the relation. So we've learned this before, that we know that the potential energy delta U is equal to minus W. So we can say delta U electric is equal to minus W. And so if you like, we can just convert that. We can say delta U electric is equal to minus Q E delta X. And in your textbook, you will use a magnitude of the difference between the distances, but I think I'll just leave it as QE. I'll just leave it as Q delta X. And then we shall say that since we consider the electric field or the electric potential energy or any kind of potential energy to be zero at the reference point, we can write, let's say that U minus U naught is equal to minus Q E delta X, and where U naught, we can say U naught is equal to 0 at the reference point. This is just like what we did for the gravitational potential energy. We took U naught, we took the gravitational potential energy at the reference to be equal to 0. Okay, so we can do the same here. In your textbook, they use the magnitude of the displacement, and so the negative sign goes away. But I'm going to keep it on this one. I see that to be more conventional, so I'll keep that, and then we go from there. So I could also write U equals U naught minus QE delta X. Okay, so let's look at the potential energy of some point charges. This is in 28.2. So let's consider the charge Q1 not Qi, Q1 fixed at some point in space, and then we move a charge Q2 from point X initial to X final as shown below. So we have a point charge Q1 fixed, and then we move a charge Q2 from X1, X initial to X final, and that charge is being moved a distance delta R using the same notation as in your textbook, and it's acted on by a certain force. So the force moves it from point X initial to X final. So this is the force of charge 1 on 2. You can call it electric force of 1 on 2. So we can say that the work done in moving the charge from X initial to X final is work. So we can just calculate work again. So the work is equal to the integral of F dot ds or dr, since we're using r, or actually let's use x since we are along the x-axis. Your book uses x. So F dot dx, X initial, X final, and we also know that the force F, which is just a force of 1 on 2, is equal to K Q1 Q2 over some distance X. So in this case, X squared. X is the distance from Q1 to the charge Q2, and Q2 moves from X initial to X final. So we can say that the work done is equal to, and in this case, again, we're going from X initial to X final, K Q1 Q2 over X squared dx. And what does that give us? So integral of 1 over X squared is minus 1 over X. Is that right? So we can say the work done is equal to minus K Q1 Q2, and then this is X final, minus K Q1 Q2 over X initial. So work can be written as, so we can say, let's actually use the potential energy. Let's convert work to potential energy. So we can say that using the relation delta U equals minus W, then we will say that delta U electric, so the electric potential energy, is equal to minus of all this, which is K Q1 Q2 over X initial minus K Q1 Q2 over X final. No, there's a negative, there's an extra negative sign. So here we have a negative already because integral of 1 over X squared is minus 1 over X. Yeah. So we have that negative. So I put that there, minus that, and then there's a plus. So now I'm taking delta U equals minus W. So I put, okay, so I have a negative. So I have, I've already turned it around. So the initial one is now positive. So minus the final.
You factor out a negative?
No, I haven't factored anything out. There is no factor. I haven't factored out yet. Remember, you see this is positive now. So it's going to be this side minus that side, which is what I have here. So now I can multiply through. So the electric potential, if I want, so I'll bring it into the same form as what is in your textbook. So if you multiply through now by the negative, then you have K Q1 Q2 over X final minus K Q1 Q2 over X initial. So this is the form that is in your textbook. And so from there, I think we can just say that the electric potential, okay, so your book has a shortcut there, but I'll show you what this does now. So we can say that since we assume that the initial potential, so we can say the initial potential 0 at the reference point, then if you write delta U electric equals U electric minus U initial, that can be written as K Q1 Q2 over X final minus K Q1 Q2 over X initial. And we are saying that the initial potential is 0. So this allows us to write the total potential energy U electric as just K Q1 Q2 divided by R, where R is just the distance between the charges. So we shall write it as X first. So if you make the assumption that X initial is equal to 0 at the reference point, then the electric potential is just K Q1 Q2 over X, where X is just going to be X final minus X initial. But since X initial is 0, then X final is the same as X. And so we can now make it a general formula as they do in your text. So we can say that, so in general terms, we just replace X by R, and then we'll say the electric potential energy in general can be written as K Q1 Q2 over R for 2-point charges. So that is for a 2-point charge system. So in our calculation of work, we are taking the work done across any path. The work done does not depend upon the path taken, because the electric field is a conservative or produces a conservative force. So the work done does not depend on the path taken. Okay, so that's an important thing to remember, that the electric field is conservative, so the work done does not depend on the path taken. So I'll make a note of that. Now this is the same as what we did for the gravitational field. The gravitational force is also a conservative force, so the work done by the gravitational force is independent of the path. Okay, so let me remind you of that a little bit. So I'll say that we recall that in the gravitational field, work done was equal to force times distance, of course. Again, we can use ds and integrate it, where the force there that you're seeing is a gravitational force. So if you recall, what we did was, suppose we take an object that is on the floor like that. We can take this object and put it on a table like that. Okay, so let's say this is a table. We take this object and put it on a table of height h, and we can say that the work done is equal to the gravitational force, which is the weight, times the height h, and that will be equal to mgh. Okay, work done is just equal to potential energy also, so we can translate that to potential energy, but this was what we did for work. We can do the same thing here. Suppose that we had a ramp of height h, and the same box was at the bottom of this ramp. We can slide the box up the ramp to a height h. Okay, and again, the work done will be equal to mgh. So it shows then that it doesn't matter how we get the box to that height h, the work done is the same. So this is what it means to say that the gravitational force is conservative, so the work done does not depend on path. In the same way, we can do that for electric field. So we can say that, let's say we have a parallel plate like that, and we have positive and negative, and electric field goes from this point to this point. If we take a charge here, let's say this charge is at initial position x1, and we take it to a point here, x2. Okay, so this is a charge q, just like we did before. The electric field is E. Okay, the work done to move that charge from this point, q1 to q2, is given by the electric force q times the distance x. Suppose that this distance is just x. Work done is F times x, where F is equal to the charge q times the electric field E. So we can say the work done is equal to q times E times x, just like that. Now, if we chose to move this charge from up a ramp, let's say we moved it from here to here instead. This is the same distance. See, this distance is still x. Okay, we moved it, instead of going along this line, we went along that line. We will still have the same work done. The work done will still be equal to the force times the distance, and it will be equal to QEX. So the work done will not depend upon the path we take. It only depends upon how far it moves along. Do you all see that? Perhaps we will talk about this some more as we go on. But it doesn't depend upon the path taken. It only depends upon the position from one point to the other. And that will be true if we went along like that and ended up here. The distance is still the same. So those 2 points from x1 to x2, the work done is always the same, whether we go in a curly way or whether we go straight from x1 to x2, or whether we go along a ramp, it doesn't make any difference. Questions up to this point? Okay, so let's look at the work done by multiple point charges before we go on. So we're looking at the potential energy of multiple point charges. So hold on a second. So we found the potential energy of 2 point charges. So U electric was equal to K Q1, keep writing QI. So Q1, Q2 over R in general. So this will be R, let's call it R12. So this is R12 to represent the distance between 1 and 2. So we can say that suppose we have multiple point charges, we can find the potential energy of these charges by, and so this requires us to assemble multiple charges, assuming that each time we put a charge in place, we fix it in place. So we are assembling multiple charges and putting them next to each other. So let's say we have a charge Q1 at this point, and then we have multiple charges at infinity. So we bring a charge Q2 from infinity to this point, and so our potential energy is now Q1, Q2 over R12 times K. Okay, so the distance from here to here is R12. So now let's bring a third charge. So let's say that we still have this charge Q1. The second charge Q2 is in place now, and we bring a third charge. Let's call it Q3. So this charge is coming from some place in infinity. And the reason why I'm using that is so that I can always say that the potential energy at the initial position is 0. And so that goes away. And so once I want to bring Q3, now I have to consider Q2 as a fixed charge. So I have initial potential energy, or the electric potential energy, would then be K Q1 Q2 over R12. This is R12. Then I'm going to have R13, and I'm going to have R23. So I have to include K Q1 Q3 over R13, and I'm going to add K Q2 Q3 over R13. So they all interact with each Q3. So they all interact with each other, as you can see. So I can now put this together. I can say that U electric can be written then as the sum of the two subscripts, and then we have K, Qi, Qj, Rij, and we don't want I and J to be equal, so I'll say that I is less than J always, as you can see there. So I'm going to say I less than J. Okay, so I have 1, 2, Ij, I have 1, 3, Ij, I have 2, 3, Ij, so I is always less than J. So this avoids double counting. So we can say that by using I less than J, we avoid double counting. Okay, let's try an example. Okay, so I release the proton. So I'm assuming that you know that the proton is going to move from the positive to the negative. So it will be repelled by the positive plate, and it will accelerate towards the negative plate. Okay, so we can calculate the speed of the proton as it travels from one plate to the other. So let me draw a picture for you. So let's say this is positive and that's negative, so the electric field goes that way. So you release a proton somewhere here, and it's going to travel and hit that plate. So the distance between the plates is d, and the electric field E is equal to 3 times 10 to the power 5 newtons per coulomb. And we know also that so we say d is 3 millimeters, and then the mass of the proton, let me give you that also. Mass of proton is 1.67 times 10 to negative 27. So I'll give you a hint. So use the work-energy theorem to do this. So it becomes pretty straightforward if you use work-energy. You remember the work-energy theorem, right? Now remember that it's released, so it's starting from rest. So initial velocity is equal to 0. So find how fast it's traveling when it gets to the end, when it gets to the other plates. And that's a proton. It's a proton. Okay, who has an answer for final speed? Okay, so remember the work energy theorem is just this. So work energy just says that the work is equal to the change in kinetic energy. So all you can do then is to say that assuming it starts from rest, and the work done, which is the charge times the electric field times the distance between the plates, is equal to half m v final squared. V initial is equal to 0, so you can just say V final is the square root of 2 QED divided by M. So I think this is all you have to do. So once you get that formula, you're basically done. I gave you the electric field, the distance between the plates, the charge, and you have the mass of the proton. So you can solve that formula. You can solve it using that. All right, let's continue. So we'll go on. Let's look at 28.3, potential of a dipole, or the electric potential energy of a dipole. So let's consider the dipole in the electric field E. So let's say we have an electric field going that way, and we have a dipole aligned that way in the electric field. So this will be a charge and a second charge. So there are going to be forces acting on this dipole. There's going to be one force this way and a second force that way. So the tendency is to cause a rotation of the charge or of the dipole that way. So the dipole lines up with the electric field. So the force is to cause a clockwise rotation so that the dipole lines up with the electric field. And we know that the torque on a dipole in the electric field is given by torque tau is equal to dipole moment crossed with the electric field that way. So we saw this earlier. The torque is the dipole moment crossed with the electric field. So we can say that the work done to rotate the dipole in the field is given by work done is dW equals torque times d theta. So we can say that work is equal to the integral of torque d theta, where the torque is equal to P cross E, dipole moment crossed with the electric field. So this is what we had when we did this earlier, some few chapters back. But in your textbook, when they do it, they put a negative sign in front of it. So in your textbook, the torque becomes PE with a negative sign and then sine theta. Okay, so we can use that approach to do it. And so with that in mind, then we shall say that the work done by the electric field to rotate the dipole in the electric field is given by minus PE, and then you have sine theta d theta, and going from perhaps an initial position theta I to a final position theta final. So this becomes minus PE, and then the integral of sine theta is a negative cosine, so we have negative cosine theta I theta final, like that. So then from that point we can say that the work done is equal to, so I'll take the negative sign out and I'll say PE cosine theta final. So let's put negative here, and okay, plus PE cosine theta initial, and then the work done by the electric field becomes PE cosine theta final minus PE cosine theta initial. So the negative sign just goes through it now, and so that's what we end up with. So this is in line with your textbook. So the only difference between what I did and the textbook was there's a negative in front of the answer. So I want to make sure that that comes up. So we also know that the work done by the electric field, W electric, is equal to minus delta U, or you can write it the other way around. Delta U is equal to minus W. It's the same thing. So we used this last time. So delta U, which is the change in potential energy, is equal to minus W, which would then be PE cosine theta I minus PE cosine theta F. And we can say delta U is equal to U final minus U initial. So I'll put the negative final in front here, and then I'll put the initial one back here. Okay, so the difference here then is that we can compare both sides, and typically we assume that the reference point is the initial, and so at that point the the energy is zero. Okay, so we can say that by comparing the left and the right sides, we find that the potential energy is equal to minus PE cosine theta final. So we are taking the reference potential energy to be zero, which means that in the term on the right side, PE cosine theta I will be zero. Okay, so that's what the term means. So we can say that in general, U is therefore minus PE cosine theta. And we know that this just implies minus the dot product of P and E. P is dipole moment, E is electric field. Both are vectors. So if you have both multiplied together like P times E and cosine theta, you can make it into a compact form using the dot product. So that's what I've done.